Well, thank you very much, Harvey, and thank you for inviting me to come and talk to your group today. I have actually visited, AREP is not probably the most automated laboratory in the world, but probably in North America. I've been to a couple of the really highly automated laboratories in Tokyo. It would be hard for you probably to grasp the enormity of what I'm about to say, but Tokyo alone has 3 very large reference labs, each of which receives 100,000 patient specimens a day and reports 1 million reportable results a day. And so if you want to see some automation, that's where to go. And I've been to 2 of those labs. At any rate, I thank Harvey for the very nice introduction. It's a pleasure to be here. This is what we want to talk about today. I was asked to talk about future laboratory automation, and so I'm not going to show videos or photographs or slides about AREP's existing automation. If you want to see that, our existing automation, there's a tremendous amount of information about it on our website, which is www.aruplab.com, and then you have to do a little bit of searching under technical expertise and then automation, and you'll find it. But there's a lot of videos that you can play of our automated transport and sorting system, our automated storage and retrieval system, the world's largest clinical laboratory freezer, at least I think it is. I couldn't get the Japanese to tell me how big that one system is they have. But what we're going to talk about is what I think is the future trends in laboratory automation, an overview of what's going on recently in clinical lab automation with more vendors and more options, faster conveyor systems, and then I want to really spend much of the time talking about how laboratory automation can impact patient safety through primarily machine vision systems, which are automated quality inspections, and I'll talk about some of these things that are listed here on this slide. So the learning objectives for this talk, since I was told to prepare some, are shown here on this slide. One is to identify and list 3 conditions that can contribute to the growth in clinical laboratory automation. 2, define the difference between task-targeted automation and total laboratory automation, TTA and TLA, and then to list at least 3 types of inspections that may be performed by automated systems replacing human visual inspections. So automation is here to stay. Probably many of you read CAP today and see the annual issue on automation that they do. The most recent issue, which was in September, if you simply count up what all the vendors claim are their automated systems that they've installed, there are more than 1,100 US labs with total or subtotal automation systems, and that's excluding an estimated 575 hematology systems. US users of automation are generally satisfied with their automation choices. Over the next several years, options for automated systems, I think, can reasonably expect it to increase along with the technical sophistication of these systems. And as we all know, the shortage of qualified medical technologists is only going to get worse. So automation and process re-engineering are really the chief ways to address this shortage of laboratory personnel. So this was a survey that was done by the Washington G2 Reports Group about 5 years ago, and they surveyed people that had automation systems, and generally people were highly satisfied. Only 3 or 4% of the laboratory managers who were surveyed said that they were not satisfied with their automation decisions. And as you could see in the footnote towards the bottom, a fairly significant percentage said they expected to add automation just in the coming 12 months, Well, this survey was done at a point in time when there was an estimated 525 U.S. labs with automation, and about 2/3 of which would be total lab automation, about 1/3 task-targeted automation. And as I showed in the previous slide, that number has more than doubled now over the last 5+ years. So going back to that CAP article, worldwide, about 2,400 total laboratories have total lab automation systems. In addition to the 100+ U.S. labs with task-targeted automation, there's another 800 labs worldwide with task-targeted automation. There's about 600 U.S. labs with automated hematology systems and 2,300 worldwide. There are 13 total vendors listed in that CAP Today article that offer either total lab automation or task-targeted automation systems, or both. I'm not going to go through a review. You don't need to hear from me about Beckman Coulter and Ortho and Abbott and all those guys. You all already know about all those vendors. What I want to do is to talk about the newer players in the field, iLAS, Labotics, and Motoman under the TLA vendor line. And I want to talk about two newer vendors in task-targeted automation systems, which would be Motoman and Sarstedt. So some of these newer total lab automation systems. This slide is a photograph of a iLAS series. iLAS is Integrated Laboratory Automation Solutions, Inc., based in Detroit, Michigan. Some of you may be familiar with Bill Neely, a well-known pathologist at the Detroit Medical Center. This is his company that he founded based on the automation systems that he had developed in his garage or his basement over a period of many years. And he turned it into a business. And his real forte is that he can put together a very inexpensive system that can serve a hospital lab. Now, it just happens that connected to that system, and I'm hoping the cursor shows up, there it is. So connected to that system is a Motoman Auto Sorter 3. Actually, there's two of them. This is one also. And the iLAS system has been installed at the MD Anderson Cancer Center in Texas, and has either one or two, I'm not sure, Motoman Auto Sorter 3s connected to down there. This system can be connected to a number of analyzers, which are listed down in here. It has point and space sampling connections to analyzers from a variety of vendors, and it's an option worth looking at for people with a limited budget but who want to have full connectivity. Labotics, David Chewell, maybe get a chuckle out of this. This is the reincarnation of our buddy Rod Markin. Labotics was a Canadian company that was purchased by Lab Interlink, which was Rod Markin's company formed at the University of Nebraska. Unfortunately, Lab Interlink went bankrupt about 8 or 9 years ago, and so just recently in this past year, we've seen the reincarnation of Labotics automation. And this is a CAD drawing of a Labotics system, but they have the ability to integrate analyzers to their conveyor system, as well as a variety of modular functional units such as centrifuges, uncapper, recapper, aliquoter, and so forth, and all of that's, a lot of that is shown in this drawing. And then a third system that I would like to show you, and this system is actually installed at the Kaiser Permanente Core Laboratory in Richmond, California. Was built by a consortium headed up by Motoman, but also including Aloka the Japanese company, and there are 6 large Aloka aliquators, which are this first row where I'm pointing with the cursor, and then the row behind it. And this is a huge pre-analytical system. It doesn't have analyzers connected to it, but it's primarily for pre-analytical sorting and processing and aliquoting. And the front line that's over here in the foreground to the right is where the hematology comes off to go to their Sysmex hematology systems. There's sorting that goes to the left that then leads to, through these aliquators, and leads to a variety of sorting for a variety of testing. One of these sorters that's back here recaps the aliquots so they can transport them to their affiliated reference lab over in Berkeley. So this has a variety of functions associated with it, and represents an initial foray of Motoman, which has been primarily an industrial robotics company, into lab automation. Here are some newer task-targeted automation systems. The Motoman Auto Sorter 3, we have 2 of these in our laboratory. There are, I already mentioned that there was 1 or 2 of them down at the MD Anderson Cancer Center. There are a couple of them at Kaiser Permanente hospital laboratories in Southern California, and the Richmond laboratory has a couple of them. And this is an automated system that can sort incoming specimens, read the barcode, determine whether or not that specimen should be centrifuged. After centrifugation, put it through a decapper, and then sort into analyzer-specific racks. There are 2 different robots operating on the deck of this, both of which are Cartesian-type robots, so they go in 2 dimensions. And so it's very fast, and it basically, its throughput is the same speed of the centrifuge. So whatever you set the centrifuge, if you're going to try to do 6 runs per hour or 5 runs per hour of the centrifuge buckets hold 24 tubes each. And so its throughput is somewhere on the order of 550 specimens per hour. The PVT company in Germany has been for a number of years making a variety of aliquoting and sorting systems, and this is one of those systems, the RSA Pro workstation. And what is unique about this one is, and I think I will refer to this later in the talk, is that it has a QS1 camera quality system which can actually look through the side of the tube as long as it's not completely covered with labels. And it can measure and quantify, or at least semi-quantify, the amount of hemolysis, lipemia, and icterus that might be in that tube, as well as determining the volume of specimen in that tube. And this is the Sarstedt DC RC900 Flex. We have 2 of these in our laboratory today, a 3rd one coming in about another month. We love these. I have some photographs of the actual ones we have. Basically, this allows for input in some sort of a customizable input tray or rack, decapping and output into analyzer-specific racks, and then a reverse operation, still with the same unit, where you can take those analyzer-specific racks, put those on the input side, recap those tubes, and transfer those tubes into a suitable output tray. So this one, which is used in our automated endocrinology section for our 25 hydroxyvitamin Ds, these yellow buckets are from large floor model head-edge centrifuge, and here are capped tubes going in the centrifuge buckets. The turntable at the back is where the decapping is, and you can't really see that very clearly. And then these are uncapped tubes going into deosorin liaison racks along here. When testing is complete, they put the liaison racks back here, and sorry, I took this photograph just as the last tubes were going through, and these are capped tubes on the output into carriers for our automated track system that have been recapped with push caps, as noted up here. This next slide is the other one that's over and serving our immunology core laboratory. And so these are just some input trays that the immunology core laboratory wanted to use, and the tubes are being decapped around the turntable in the back here, and then the output is going into quantometrics racks. They also are outputting into FACB immunocap racks. I didn't mention that the other one that's over in the automated endocrinology also has a drawer, can be fit with a different drawer, so it can do Abbott Architect racks, and all of these are customizable. You simply choose the racks that you want to use. And then here's the output quantometrics racks coming back into the carriers for the track system to go back to storage. In this case, this particular model is applying not the push cap in recapping the tubes, but is applying a screw cap. So the same screw cap that we use on our Sarstedt tube today is what's being put back onto that tube. So we really like these units. They're very flexible. They're very quickly to set up and operate. The other feature of new clinical laboratory automation that I think is worth noting and talking to you about are in two areas. One is new track technologies. Both of these companies, FlexLink and MagnaMotion, had exhibits at this past summer's AACC meeting in Anaheim, and I'm sure they'll be at the next AACC meetings coming up. Compared to our track system that we operate at ARUP, which can transport 2,000 specimens per hour on any given stretch of track, the FlexLink X45 conveyor can transport 3,000 pucks per hour, so it's about 50% faster. And the pucks are automatically, or the system comes with the pucks having RFID chips in them, which it really makes it very useful for identifying the pucks on the track and for routing the pucks to the correct delivery address on the automation system. The other one is from a company called MagnaMotion, which is a relatively new company started up by 4 engineers from MIT, and it's called the MagnaMover Light Transport System, and it's using linear synchronous motors and magnetic pucks. So I'm sure most of you are familiar with bullet trains and people movers and things like that are using maglev technology, where the system employs repelling magnets so that the moving vehicle rides on a layer of air and there's no friction with the track. This is sort of the opposite, but similar in a sense. So the pucks are magnetic. The motors are hidden inside the track. In a 1 meter section of track, there are 60 small motor coils, and so the magnet is repetitively attracted down the track from one coil to the next. This is the system we've chosen for our track of the future that we're going to be having custom built and with all new robotics and all sorts of stuff. So this system is 9 times faster than our present track. A given section of track could transport at full speed up to 18,000 pucks per hour. The other area where I want to spend most of the time today is in automated inspection systems, or what I call machine vision. And these include inspections for tube type and tube size and cap color, inspections for volume, both total volume and the volume of serum or plasma above a packed clot of red cells, inspections for fibrin or hemolysis, lipemia, icterus, and so on, and inspections for mislabeled specimens. I think this is an area where clinical laboratories will make considerable progress over the next decade, and an area in which we can really address the shortage of trained medical technologists. This is the FlexLink track, and it's really very slick to see this live. These conveyors move very quick. These are some of the actual pucks, and they have all sorts of mergers and diverters, as you show here with just a little grabby thing. We can play that one more time so you can see how they just will feed these things onto different lines or go around mergers and diverters and that sort of thing. So it's a very slick system. The MagnaMotion one is the one we've chosen for our future automation. For a new building that we're going to be building, and this should be going live in about 3 years. And as I said, these are magnetic pucks gliding around on stainless steel track. Very, very fast, very smooth, and what you'll notice is no moving parts. When our bioengineers heard that their only maintenance was to dust it off once a month, they were kind of excited. So this is the MagnaMotion system, and just a couple of CAD drawings of what the system might look like in the laboratory, and I already showed you the video. So let me conclude this part of the talk with a slide that I borrowed from a consulting company called Argent Global Services. This is not a David Letterman list, but sort of like that. Top 10 reasons why automation projects are not successful. Too often laboratory managers just don't have a complete understanding of what their current environment is, the processes, the costs, customer expectations. And so that creates a false understanding of what they might expect out of an automation system. Laboratories sometimes lose flexibility in their operations when they put in automation because of fixed processes that are associated with that automation and because of the limited throughput that they get. Managers may have an unrealistic expectation of the system in terms of the cost reductions or the throughput or the return on investment that they may achieve. There may be unplanned or poorly developed workarounds that are required to interface the automation with the manual processes in the laboratory. Unclear expectations of system functionality, overbuilt and unnecessarily complicated system designs, inadequate technical support, a credible and realistic impact analysis might not have ever been conducted. There can be hidden costs such as labor, supplies, or maintenance associated with the new automation. And the biggest mistake, I think, is the failure to optimize their current processes and do process improvement before doing the automation. This is something that I've always preached in all of my lectures, that if you automate a poor process, you still have a poor process. So I'm a strong believer in several processes that a laboratory should go through when they're implementing automation. And the most important of those is workflow mapping. And you can do workflow mapping with material flows such as specimens or process flows. You can do data flows. You can do workload maps. But I think doing workflow mapping is extremely important to understanding your processes before you engage in designing an automation system. We did this extensively in 1996 before implementing our current automation, which went live in 1998. We've been doing it for the past year as we get ready for our new automation. And we have not even attempted to send out RFPs for vendors and designing systems and even choosing the track until we had done all of this mapping, which was done a little over a year ago. Here's an example of a workflow map in which the receiving department in this particular laboratory is receiving 8,500 specimens. Of those, a certain number go directly into hematology testing, that's 2,500, and then another 1,600 are going to urine analysis, and then that leaves 4,400 over at this point, and some of them go through centrifugation and some go around and are not centrifuged, and you can see after centrifugations another 400 are going to coag. So you can draw a map like this, determine the number of specimens that are flowing through your operation, and this really can help you in planning your workflows and planning what kind of automation you might need. Another important step, I believe, is identifying possible solutions to meet needs. Using re-engineering of processes, as I said, using quality and turnaround time measures, workflow and timing studies to find the bottlenecks. I don't necessarily believe that the process improvements in a laboratory have to involve automation. And you can gain a lot from some small re-engineering projects compared to the implementation of an expensive automation project. And as I already said, automating a poor process still leaves one with a poor process. These were things that we did when we re-engineered our processes. We use a number of continuous quality improvement tools, such as Lean and Six Sigma. We standardized our processing procedures to a best practice. We have reduced or eliminated non-value added handling and sorting. We primarily were interested in eliminating running around to find shared specimens. All too often in a laboratory, a specimen has to be shared between two different testing sections. The section that gets the specimen first gets their work done on time and everything's cleared off of their pending list. And it's the second laboratory section that's supposed to have that same specimen that's stuck with the job of running around the laboratory trying to figure out what happened to that specimen. Evaluating alternatives, potential progress measures. We use most of these. We don't do stat specimens, so we don't measure stat turnaround time in our laboratory because we're a reference laboratory. But we measure our turnaround time both at median and 95th percentile. We constantly measure lost specimens, mislabeled specimens, and we look at some productivity measurements that I've indicated here. So here's a plot of turnaround time, and this is for all specimens at ARUP. The baseline is the time. Along the left side, you can see 0% of the tests going up to 100% of the tests for whatever that total number of tests are for the given calendar year. And so 50% would be like a median turnaround time. And so you can see that if you just follow the years over here and follow the colors, that each year the curves continue to move towards the left, meaning that the turnaround time is getting shorter. And you could see the same thing at the 90th percentile, or you could see it at the 95th percentile, and so on, that the curves move progressively to the left, meaning faster turnaround time. This is a lost specimen chart, and I've been tracking this for many, many years. And this is a log scale, as you can see down the left side. And I plot lost specimens per 100,000, total specimens received. And you can see that this has been a very steady improvement. This green dashed line along the bottom is the level for Six Sigma performance, which is 0.34 per 100,000 or 3.4 per million. The red line was 5 Sigma performance. Now, our quality department at ARUP actually plots this as per 100,000 build units, because every build unit on a specimen is an opportunity to lose the specimen. And so actually some of these points that you see down here actually are at 6 sigma levels when you do it on a build unit. However, our build unit system changed in about 1997, and so I wanted to go back and show the old numbers that I had been collecting, and the only way to do that was to do this on a total specimen basis. But at any rate, there's a tremendous amount of improvement, as you can see, over that period of time. Now this is a chart that I got from Bonnie Messenger, our quality manager, before doing this talk, because it's the same data from the previous slide, but plotted in a much different manner, and it's also it's processed as a process sigma. So it's using the Six Sigma statistical model that she follows, and what she's tried to do is to show that different initiatives, different things that have happened in the laboratory operation have influenced the improvement of this data. And so here you can see a major automation system that we upgraded to at the end of 2003, beginning of 2004. Here's another process improvement, missing sample checklist change. And then just in the past year, we started to go to a pod system, which is a team system in specimen processing. And that has resulted, that point there is kind of reflective of this point over here. And this is a productivity chart that I have tracked over the years, and since we've implemented automation, our productivity has more than doubled from the neighborhood of 4,000 build units per technical employee per quarter to more than 8,000 per quarter at the end of the last fiscal year, and last June 30th. So let's talk now the remainder of our time about machine vision. And what is machine vision? If I can begin with a definition of it for you. Machine vision systems are automated systems for the rapid inspection of products or items that replaces human inspection. These can be cameras, these can be lasers, x-rays, gamma radiation, infrared, visible light spectrophotometers, just a variety of technologies that are going to replace the human eye, who's going to pick up a tube or pick up a specimen or pick up a bottle of ibuprofen or whatever, and know that it's correct and has been packaged or handled properly. Most consumer products that you purchase today were manufactured by processes that use machine vision. So here's a brief list. This is by no means comprehensive. I'm not going to read all of the things that are on this list, but if you have a bottle of water that you bought from the store, it's got barcodes, it's got expiration dates, it's got lot numbers, there's all this type of stuff, and all of that kind of information can be captured in machine vision systems. The bottles of water are packaged into some kind of a package, and there are camera systems that assure that the packaging system is working correctly and the package looks nice and neat, because if you're the customer, you're not going to buy it if the package looks goofy. And so on and on and on and on, there's the list of stuff that machine vision systems are doing for us. Here's a few examples in this slide. Inspecting quality of cap closure, inspecting for overfill or underfill in a bottle. You can see here an underfilled bottle. Inspecting for a torn label, which is, this label is torn right here. Inspecting the label quality, date and lot codes. This is my favorite. So here's a little glass shard in this jar of orange marmalade that was picked up by X-ray. And I'm sure glad that somebody, whoever this company is using that. This is a video that I do want to play, and what you're going to see here, this is from an Anheuser-Busch bottling plant in St. Louis, Missouri. This is one of the world's largest breweries, and they're a large 8-story bottling plant. When I started working in machine vision a few years ago, I was really trying to learn a lot about it in other industries because it had never been tried in machine vision systems had not been tried in clinical laboratory. And I'm from St. Louis, and so it was a natural for me to call up a local establishment for which I had high regard, and I was able to establish a relationship with the director of packaging quality and technical services, and I just said, is it possible that you have any file videos or whatever that you could share with me? Well, they didn't. To make a long story short, Anheuser-Busch brought a film crew into the canning plant and made videos for me for my lectures. And I thought it was a wonderful thing that they did this. And so you're going to see this video. Now, not only that, I need to explain that the cans going by on this system are going by at the speed of 1,000 cans per minute, faster than the human eye can see. And so since the first videos didn't turn out very well, they brought in a strobe light system and used a strobe light so that you could really see these better. So my first lecture, I think I did this to an AACC audience, and I said, gee, I hope you all go out and when you're having dinner tonight, have an Anheuser-Busch product to thank this company for their public service mindedness. So anyway. That's the actual sound in the factory. But you're going to see these cans going by, and this guy has just pressed something on a computer, and an underfilled can is going to pop out into his hand. Now that speed of 1,000 cans per minute is, they're able to do this with gamma ray detection systems that are precise to 0.05 ounces. And as you know, a standard can of beer is 12 ounces. So if that can of beer is 11.95 ounces or left, it rejects it. Now, here's a clue. California does not allow underfilled cans. So in California, that range has to be between 12.0 and 12.05. So if you want to buy your beer in California, you're always on average going to get a little bit more per can. But anyway, I did ask the fellow what happens to the cans of beer that the system rejects, and he assured me that the quality department gets them all. Nobody gets to drink them. But anyway, I was learning a lot about the concept of machine vision, and this was really valuable to me, I thought, to understand what we could do with machine vision. So in this system, this device right here is actually this gamma ray detection system that's going by and that detects it and instantly kicks the can out that's underfilled. And we can talk about where machine vision systems are coming into the clinical laboratory. And one of those areas is it can be seen in Beckman Coulter's Automate system. This has been out for several years, this system, but it has the capability over on the right side of the system to pick up a tube, look through the side of the tube, actually through the labels. The tube doesn't have to be unlabeled, and it can tell the difference between packed red cells and the serum and estimate the serum volume. So it then knows how much volume is available for making aliquots. This system from Motoman has a camera system over here in the corner where I'm pointing the cursor, and it can look at the tube type, the size of the tube, the color of the cap, and then compare that information to what its expectation is based on using the barcode and querying the LIS, so it knows it has the right tube for the test that's been ordered. This is Olympus, and as we all know, Olympus is now part of Beckman Coulter. But it's the same concept. Here it's looking through the side of the labeled tube, and it's measuring the volume of serum above the, in the tube that's been centrifuged, above the packed cells. And I already mentioned the PVT workstation, and it can do the size and presence of the stopper for decapping and recapping. It can do sample type by tube size and cap color. It can compare that information to what it's expecting from the LIS. Liquid level detection, volume calculation, hemolysis, lipemia, icterus at 3 semi-quantitative levels for each. This one, however, cannot go through the labels. It does require 6.5 millimeters of unlabeled tube window to work. So this is from the PVT system, and over here it's showing these indices and quality parameters on the specimen, and that's the photograph that it's taken of the tube as it's doing this. So I'm going to talk a little bit about some machine vision, and we're running out of time, so I'm going to skip this collaborative project with our College of Engineering to develop a system for measuring minimum and maximum volumes, and just talk about the mislabeled specimen project that's been a research project of mine. Mislabeled specimens are a serious problem in the United States. A CAP cube probe study that was published in 2008 for 147 labs that were willing to participate in the cube probe study showed an average of more than 1 mislabeled specimen per 1,000 specimens received in those laboratories. And a similar cube probe study just recently published this past fall, and I didn't update to the actual citation, but it was just, I think, September issue of the Archives of Pathology and Lab Medicine. The blood bank error rate was in excess of 1%. These are horrendous numbers, which should scare all of us if we have any of our own specimens going through laboratories for testing. And at ARUP, our error rate is not that bad. It's about 1 in 10,000, but that's still very unacceptable to me, and I think to anybody else. Even though our downstream inspection processes catch 96% of the errors, we think, that still leaves an error rate of about 1 in a quarter million, in which a result goes out the door on the incorrect patient. And I think that's still unacceptably high. So about 5 years ago, I started working on developing a machine vision system that could use high-speed cameras and try to do optical character verification and identify if our employee had mislabeled the specimen. And we're making some pretty tremendous progress. Now this video will play out of the PowerPoint. So this is still a prototype system that's in research. Here you see specimens coming down our conveyor system. Here's one of the cameras. Here's one of the cameras here. The other 2 cameras are around behind these other 2 panels. And the robot picks the specimen up momentarily in front of the 4 cameras, and we take 4 photographs. And then the software assembles the 4 photographs into a single photograph. So basically, you've taken the outside circumference, the outside of the tube, and you've unwrapped it from a 3-dimensional image to a 2-dimensional image. So now this view is from the conveyor towards the thing, and now here's a different view. There you can see 2 of the cameras. You can see a close-up of the robot. We're going to be replacing the robot later this year with something other than a vacuum lifter. It'll be more reliable. Here again now from the side, you can see how there's 2 of the cameras, and you can see it's picking up a tube. Now watch this screen up here in the corner, and you'll see every time that thing picks up a tube, this image changes, and that each time that's the new photograph. That's how fast this system is. It's able to do this analysis in 2 to 3 seconds per specimen. Now, you can't see this for HIPAA reasons. It's been intentionally sort of blurred by our audio-visual guy so that you couldn't see this. And but now I'm going to show you some examples. So this is an ARUP label, a hypothetical patient named ARUP test, St. Mary's, and it just simply shows that what we've done is put this little black square on the label as an fiducial mark, an index mark, so that the software can find the patient name on the label. And the combination of that black square and this barcode, and the system then knows, okay, this is the outline of the ARUP label. So it then is going to take this barcode, query our LIS, and find out the patient name associated with it. So here you see what that operator screen looks like. And here's the ARUP label across here where I'm pointing the cursor. Test patient, space, pathology. This green circle is surrounding the little black square. This green outlines the barcode. It queried the LIS. It takes that patient name that had a comma and a space and just converts it into a continuous character string. And then it looks outside the zone of the label, because here it knows that's the top edge of the label, and it tries to find a matching character string, again dropping the punctuation and spacing, and see if it can find a matching character string. And this is an example of a pass. It says down here, inspection result, inspection pass. Here's an example of a fail, because I intentionally typed on the ARUP label and S as the end of the middle name. So test, ARUP males, but we had a customer make these labels up for us so we could have a different fonts and all that sort of stuff. And so the customer had just typed male, and so the system saw that as a fail, which was the correct way for it to see that, and so on. So this project is coming very close, and I think sometime in the next year we're going to be going into what I call a high volume phase of the research. That is to say, we'll have a good robotic system, and we'll be running thousands of these every day and accumulating the data on the performance of this system. But it's still very much an R&D project. However, when we build our new building, put our new track system in, that Magnum Motion system that I showed you, and our plan is to have a half a dozen of these camera systems installed on that, and every specimen going through ARUP on the track system will be photographed and inspected with this label inspection system. So that's our intent before we go live with it, is to run at least 1 million images through and get the actual statistics on true passes, false passes, true fails, false fails, and so on. And we think that we're going to eliminate that 4% of errors, or 4% of that 1 per 250,000 of errors that we think are going out the door. So we want to minimize the number of tubes that fail due to label quality, font training in the OCV system, people putting the ARUP label too close to the customer label and blocking part of the patient name, a variety of reasons like that, where the specimen's correctly labeled, but the system can't see that it's correctly labeled. And so if we can minimize false fails, we'll minimize the manual work that's required. We absolutely have to be able to guarantee in this system that any mislabeled tube will definitely be caught. And the way the whole thing will work is, once this is on the automation system, anything that the computer can't pass is going to go to a lane where a human will inspect it. So with the work we've done up to this point in time, we're at about an 80% well, we started out at about an 80% failure rate. We got that up to only a 30% fail rate, and then the most recent work that we've done is at about a 20% failure rate, and there are still some of these things that we can work on to improve and get that even better. And if our objective is to get it up to about get it down to about a 10% fail rate or a 90% where the system is passing it, so that only 10% of our daily workload of, say, 50,000 specimens a day requires human inspection. So in summary, progress is being made to develop a machine vision system that uses optical character verification to rapidly inspect patient specimens for patient name labeling errors. And this technology does appear feasible. It's not something that we can patent. The camera company has got umpteen patents, and just because, I mean, they've patented for every kind of item going down a conveyor belt in a factory or a bottling plant, and the fact that we're using it for specimen tubes does not represent a difference from the kinds of applications that they've proposed it for. And then finally, what is going to help us in the mislabeled specimen arena as well is that there is a CLSI standard that's going to be coming out in April on label formats, specimen label formats, which is going to, amazingly enough, have all of us have all of our labels look the same. And they'll all have the same fonts and font sizes and formats, patient name in the top left corner. Everybody's going to hold the tube the same way, stopper in your left hand, tube reads left to right, and so on and so forth. Amazing that we've never done that in our industry. So that is coming this year. These are some impacts of automation at AREP, because I've talked about some of our systems. Tremendous amount of growth, tremendous improvements in turnaround time, reductions in lost specimens, productivity more than doubling. And so this is a final slide, a summary slide, which about the growth of clinical laboratory automation. I think everybody knows the reasons why automation is growing, the shortage of medical technologists, the baby boomers are causing more lab tests to be done, and the automation is continually getting better. There are both task-targeted automation systems and total lab automation systems that are having tremendous value in the laboratories in which they're installed. And there's a variety of machine vision systems that are coming that are going to be very effective, I think. So, thank you very much for your time. I appreciate it. Maybe I can answer some questions.